All right, so what I'm going to do is do a rundown of what our methodology is here. And so we're going to be looking at a spring system with damping, and we're going to use Euler's method to have a way of graphing this. We'll get deeper methods as we go further, or at least call deeper methods. But right now we want to transform this into something that's going to be useful for us. And one of our techniques that we're going to do often is we're going to divide out any leading coefficient so that this transforms into y double prime plus b over m y prime plus k over m y equals 0. But right now we're looking at the homogeneous case. We can very easily add driving forces to this, and we will. Also, the sign here will get absorbed by the constant. So this is truly damping, and you'll have a negative b on there. So I'm letting the sign be absorbed by the b constant. And so I'm just keeping these things positive. And what we want to do then is look at how we can solve this equation and what we're going to be able to do to solve this equation. Sorry about that there. Make sure. Yeah, okay, that's what it is. And we're going to look at Euler's method, and what we're going to first start with is, well, we can find, giving initial conditions, position. And so for our method to work here, we're going to need a full set of initial. This is an initial value problem. So we're going to have an initial position and an initial velocity. So I guess I'll put those over here. We will have y 0, or y at time 0 equals y0, and y prime at 0 equals y prime 0. That'll be our initial conditions that we're going through. Well, if I'm looking at position versus time, and for now we'll say we're starting at the origin, I have an initial place here. Well, first order differential equations, I could take the first order differential and say that was the slope. And that would tell me where the next positional piece would be. I can do the same thing here because this position is going to change based off of its first order term, which is going to be the velocity. And so I can take the velocity as a slope, and I can move some time step h over and have my next position, y sub 1. What we want to do is we want to take that same mentality and apply it to y prime as time goes forward. And so we have an initial condition for y prime. Let's say we are here, and we want to apply some function to it so we can get the next position. We're going to, by analogy, borrow the same idea. And we can make a variable transformation here that'll help us. We can say, let y prime equal v. And so y prime will be our velocity term. Then in y double prime is v prime. And v prime is going to be a function of t y prime and y. In fact, v prime will be this term. If we picked up all these things and moved them to the other side, these determine our slope field at a given point. And so what we can do is we can use these terms to get a slope for how v is changing. And we can update v, and mostly negative here. We get our new velocity term over the same time step. These are both happening at the same time step. And now I have two new initial values. And I can repeat the whole process, so I can loop. And so what we're going to do is we're going to use Euler's method to put this together. And we're going to look at this as what we would need to do. So I'm going to sketch it out mathematically here, and then we're going to look at some pseudocode on the other side of the board here to do this. But mathematically, what we're kind of looking at is, if I want to know my next position given some time, well, that's equal to my current position plus a time step times my current velocity. And this is exactly what we did for Euler's method, except instead of saying velocity, we said it was the differential equation, but right-hand side, because that was defining the slope field. Well, in this case, that is the velocity term. And so we move some time step by the velocity. But at the exact same time, we have to update our velocity so that our next velocity term is equal to our current velocity term plus h times the function here. And so for our damp spring, that function, let me just do a quick functional rewrite here, is y prime is equal to negative b over my prime minus k over my. And so I will have negative b over m times, well, y prime is the current velocity. And then minus k over m, well, y is the current position. And so Euler's method lets us, in pairs, update both the position and the velocity terms. And so now we're able to work our way through a whole series of steps of these to see how our differential equation, our spring system, is changing over time. So let's pull that over on the other side here. Alright, let's flip it down. I already have this done like a Blue Peter episode, but we'll erase this and pull this back out. So let me do spoiler alerts. We'll build some pseudocode here. But I'll keep the framework over there. So this is the framework that we're working with. Those are the equations we just worked out. And we want to make some pseudocode over here to do this. And this is, again, pseudocode. It won't run in any particular programming language. I think when I wrote it, it was very close to running right off the bat in Octave or MATLAB, as is. But what we're going to do now is we're going to write our pseudocode and make it work for us. So first thing I need is initial conditions. Now, we always found we had to keep track of the time variable. So I'm going to have my initial time, some array, element 1, 0. I'm going to have my initial position. And again, I'm going to do the same thing here. I'm going to start at the origin. Actually, I'll do what we do with most springs. We'll displace it one amplitude, but we'll release it with no velocity. So my initial velocity will be 0. So this is a model of, if we think of a spring, and my displacement, I pulled it over to whatever the amplitude is, and I'm letting it go. So there's no initial velocity, but there's the initial displacement. And so the restoring force will drive the kinematics from this point. So we have our initial system set up. We have everything in there, and we'll probably need to define our time steps and our number of steps. And I go by the number of calculations I want to do. So I'll do, you know what, I'm going to do 100,000 calculations. No, MATLAB screams around there. So we'll do 10,000. See if we don't kill MATLAB's memory. We'll do 10,000 calculations. And so our time step is going to be however far we want to go ahead in time. Now, I don't know how this system evolves, and I might need to come back in here and change what my initial time is or final time is. So probably somewhere up above I'd make a place where I could define my final time. And my initial times are going to be zeros. So TF minus T1 divided by the number of steps. And that's going to give me the size of the time step I need to work through. All right, now I need to just create these values. So I'm going to make a loop for k in 1 to n. I'll define my loop for k to 1 and n. Again, this is more MATLAB-y. And I'm using k so I can just take the math I did and bring it down over here. So I can say y of k plus 1, my next y value, is going to equal my y of my current y value plus h, which was calculated up here, times my current velocity value. And this will update all of those. And so my big thing here now is to update my velocity component. And so my v of k plus 1 equals my current velocity plus h times, and here I think I might expand the math out a bit. Let's see here. So I think I'm going to distribute the h through, so h times b, and I brought the negative sign through, so I'm just distributing the math through, divided by m times whatever my current velocity is, minus h times k divided by m times whatever my current position is. And we've done it. We've created code, pseudocode, that will plot our second order differential equation. And it will work its way through and update it. And then once this loop finishes, we will get on the other side, for MATLAB type stuff, what do we need to do? We need to do t k plus 1 equals t of k plus h, right? To do our plots. And now I can plot position versus time. I'll get my sinusoidal pattern. I can plot my velocity versus time. I can even plot my velocity versus position. And that's our method. Now we just gotta try it.